For my project, I created a library in the JavaScript language for creating, manipulating, and analyzing graphs. I've made the code available publicly here on GitHub. You can see the URL here at the top. It's also linked in the written report under the citations. So first, some background about why I created this library. As far as scientific computing and computational mathematics are concerned, the Python language has really emerged as the preferred language. And this is largely due to the variety of mathematical libraries that are available for the language. Some examples of popular libraries for the Python language, which you may have heard of, include NumPy, Pandas, SciPy, Matplotlib for plotting, and scikit-learn for machine learning. These libraries have seen widespread adoption across various industries. It's really the availability of these high-quality libraries that have enabled Python to emerge as the preferred language. And this has resulted in really a shortage of mathematical libraries for other competing languages, since most of the focus has been on Python. I chose to create this graph theory library for the JavaScript language for a variety of reasons. One, just due to its prevalence on the web, and the fact that it's available in every web browser. So having high quality mathematical libraries available in the JavaScript language would allow more widespread adoption of these tools. Accessing these tools would be as simple as visiting a web page rather than needing to get into the technical details of installing Python and the various libraries and then running the Python code. It lowers the barrier of entry for using these tools and applications that make use of these tools. Another benefit of making libraries like this available for the JavaScript language, it relates to the fact that JavaScript is so widely available on every web browser, is that it would allow resource-intensive tasks that traditionally are performed on a server or in the cloud could now be run on the client on the user's web browser. This would help to reduce costs for businesses by eliminating the need for maintaining and running servers and cloud instances, since the code will be able to run directly in the user's browser rather than on an expensive server. The code for this library is all contained in this JS Graph Theory file. I'll walk through the code a little bit later in this presentation, but for now I'm going to show a demo of how you use the library. So I've got a file open here. It basically is just importing the library here. There's no graphs have been created yet, so that's what I'm going to do here. I'll start by creating a graph by calling new JS graph. This just creates an empty graph with no nodes or edges, just an empty JSON-C list. Now I can add some nodes to this graph, so I'll do graph.addNode. Then you specify the node ID here. In this case, I'll give it an ID of 1. I'll create a few other nodes for this example. 6 nodes there. So now I've got a graph on 6 nodes. So yeah, there's no edges to this graph yet. It's just simply created a single graph here and added 6 nodes. So now I'll call this function graph.displayInfo. Just see some basic information about the graph that we just created. Now, when I run this code, you can see got a graph of size 0, order 6, with 6 components. And that's because I just added 6 nodes and no edges yet. Shows a list of nodes that are adjacent to each node, and so far there's none. And this is the basic graph data structure up here. It's an adjacency list. And you can see there's six nodes, no adjacent nodes yet. So now I'll add some edges to this graph, which is just graph.addEdge. And here you just pass in the nodes that are connected by the edge. So here I'll create an edge that connects nodes 1 and 2. Create another edge here that connects nodes 1 and 5. And create a few more here. This one connects nodes 2 and 6. Nodes 2 and 3. Nodes 2 and 4. Nodes 3 and 6. I'm adding several edges here for when I demo the Fleury's algorithm for finding an Euler circuit in this graph. 3, 4, 3, 5. Just adding a variety of edges here. 5, 6. All right. So we added a bunch of edges that connect various nodes. And now when we run this code, you'll see we have 11 edges. So the size of the graph is 11, order 6, and there's one component because all the nodes are connected. Now this list shows the nodes that are adjacent to each node. Node 1 is adjacent to node 2 and 5, and so on. And the data structure has also been updated, the adjacency list. And now I'll run Fleury's algorithm on this graph. So I'll do graph.algo_Fleury. And this algorithm will just find an Euler circuit in the graph. So I'll log that to the console. Now, when I run the code, you'll see here it's found an Euler circuit starting at node 1 and ending at node 1. And that's run using Fleury's algorithm. And I'll go through that algorithm here in a minute as I walk through the code base. Now I'll demo removing nodes and edges. So here, for instance, you can see node 2, it's adjacent to node 1, 6, 3, and 4. So I'll start by removing node 1. And that's just a graph.remove node. You specify the node ID. And you'll see now the graph is order 5 instead of 6, so it's removed node 1. And in the adjacency list, you'll notice that all incident edges have also been removed. So I'll add that node back. You see it's there, order 6. Now I'll show how to remove an edge from this graph. You just do graph.removeEdge and specify which edge you want. So I'll remove the edge between nodes 1 and 2. And when I run the code, previously it was size 11, and you notice node 1 is adjacent to node 2 and 5. So when I run this updated code, you'll notice the edge has been removed, so the size is reduced to 10, and the adjacent edge between nodes 1 and 2 has been removed. So now I'll add that edge back. Alright. So now I'll show one of the utility functions. It's graph.isAdjacent, and it determines if two nodes are adjacent to one another. So I'm checking here if nodes 1 and 3 are adjacent. I'll log that to the console. Now when I run the code, it returns false. Those nodes are not adjacent, as you can see here, but nodes 1 and 2 are, so I'll set that to nodes 1 and 2, refresh the page, and now it's returning true because those nodes are adjacent. The next function I'll demonstrate here is getNeighbors, which returns all the neighbors for a specified node. So here I'll call getNeighbors on node 5. And you'll notice it just returns all the nodes that are that are adjacent to node 5. Next function I'll demonstrate, functionality really is setting a value for a node. So far we've just used node IDs and not actually specified a value for the node, which can be useful in various algorithms. So to do that, I'll call graph.setNodeValue, and you first specify the node ID, which here will be 1, and then the value, which I'll make 400 here. And then to return the node value, you call graph.getNodeValue, node 1, and now when I run the code, returns the value of 400. Another function, there's a variety of functions available in this to get the order of the graph, the size of the graph. Another function I'll demonstrate here is graph.getDegree, which just returns the degree of a node. So find the degree of node number 4, which is 4. Degree of node 1 is 2. Another function that's available counts the number of components in the graph using depth first search. So to call that function, it's graph.countComponents, and that just returns the total number of components in the graph. In this case, there's only one component. Another function that's available is the isBridge function, which determines if an edge is a bridge or not, and it does so by removing the edge from the graph and then determining if the number of components has increased or not. So I'll call isBridge on node 1. It returns false. And actually, here I have to specify the edge, so I'll check the edge between nodes 1 and 2 to determine if that's a bridge. Run the code, returns false, so that's not a bridge. However, you'll notice there's only 2 edges connecting to node 1, so if I were to remove graph.removeEdge, which I showed earlier, the edge between nodes 1 and 5, this edge between 1 and 2 becomes a bridge. So when I run the code, it returns true. And like I said, it determines this by just removing that edge from the graph and counting the number of components, determining if the number of components in the graph has increased or not. Right, so now I'll just do a quick walkthrough of the code. I mean, like I said, this is all available on GitHub. The URL is right here, github.com/NathanK/graph-theory. And it's also linked at the end of the written report in the citations. But yeah, here's the GitHub repository. It's just got the graph theory libraries, this .js file, and then test.html is the demo I was showing you. So open up this jsgraphtheory.js. I'll just do a quick walkthrough here. All the functions here are documented. So this JSGraph function creates an empty graph, but it also has the ability to clone an existing graph just by passing in an existing graph, and I can show that. Let's say I want to clone this first graph. I create another graph. Graph2 equals new JSGraph graph. So here I'm creating a new graph called graph2 and passing in this original graph when I create it, and it's essentially just cloning the graph and creating a copy of it. This is just a function used internally for displaying error messages in the console. Here's the add node function I was talking about. We pass in a node ID and an optional node value, and it adds a node to the graph. Here's the add edge function, where you pass in an edge array, which is just 2 nodes that are connected by an edge, and it adds the edge to the graph. Here's the function to remove a node. You just pass in the node ID. So remove node and then pass in the node ID. Remove edge, once again pass in the edge array, which is just an array containing the 2 nodes that are connected by the edge, and it's updating the adjacency list. Here's a function to determine if 2 nodes are adjacent or not. This function, getNeighbors, returns all of the neighbors of a specified node. GetNodeValue, which I showed, returns the value of a node. SetNodeValue. GetOrder returns the order of the graph. GetSize returns the size of the graph. This getDegree function returns the degree of the node. I demoed all of these, but this is the code that powers those functions. And like I said, it's all available on GitHub if you want to take a look. Display info just displays some general information about the graph. Count components uses depth first search here to determine the number of components in the graph. Here's determining if an edge is a bridge. The isBridge function, you pass in an edge and it determines if it's a bridge, and it basically just removes the edge and then counts here. It counts the number of components to determine if the number of components has changed. And then this is Fleury's algorithm here for finding an Euler circuit. Pretty standard algorithm that I've implemented here in JavaScript. First checks if the graph is connected, and then it checks if all vertices are even degree, and then it runs the algorithm and returns the Euler circuit. So that's the code base. JavaScript. It's all available at this repository if you're interested. It's about almost 400 lines of code, but it's all documented in here. Every function, is described. Code's commented out, so it's pretty easy to follow if you know JavaScript. If you don't know JavaScript, might not make a lot of sense, but it's all here, commented. So yeah, check it out if you're interested. It's this is the URL up here at the top, github.com/NathanK/graph-theory. And again, it's linked at the end of the written report under the citations. So yeah, that's the library. Again, my motivation for creating this library was just to make kind of, I guess, fill the gap in some non-Python languages as far as mathematical libraries that are available. Um, JavaScript's an important language given its prevalence on the web and availability across every web browser. As far as future ideas go, the library could be extended. Additional algorithms could be implemented. It's already been publicly released here, but could add other features like graph visualization. But yeah, it's a solid foundation for a graph theory library. It's got the data structure in place, all the functionality you need for managing um, and graphs, and shows the adjacency list for computational efficiency and running various algorithms. But yeah, really any number of graph theory algorithms could be implemented and added to this library. It's currently, I guess, I was sitting at almost 400 lines of code. But yeah, it's got what you need to work with the graph data structure, and analyze and run Flory's algorithm on the graph. So that's my project. Code's all on GitHub. Yeah. Thanks for watching.